All right, so please introduce yourself. Who are you? Thanks for coming on Channel 9.
Sure. I'm Michael Fortin. I run the Windows Client Performance team. So my team is kind of responsible for the end-to-end performance of the product, whether it's booting the system, doing the normal standby hibernate type power state transitions, or actually running applications, browsing the web, or any of the audio, video, media type performance experiences as well. So pretty much all things performance. We work with a bunch of partner teams on that effort, so there are performance people focused on a lot of different features, and they work with us, we work with them to ensure that the whole product is kind of done that way. We also have a set of development projects on the team as well. So one of them is SuperFetch, which is kind of a new way to manage memory, and we can get into some detail on that a bit. There's a few other technologies as well that are developed on this team. ReadyBoost, which is I guess it's a USB key type thing where you plug this in and it's got flash on it, and we use that to extend memory management and try and improve performance by that. Another is the ReadyDrive technology, which is the hybrid hard drive, so it's got a pool of flash along with the normal track buffer that exists on the drive, and we manage that as well. There are two other things, the Windows Experience Index, so that thing that prints the number on your machine, it's a 5, it's a 4, whatever, we do the work behind that. And then there's some built-in diagnostic capabilities into the OS as well, and we've been building the performance aspects or the performance-focused features that go along with the diagnostic infrastructure.
Interesting. Now, these diagnostics, are they, is Windows actually using the information in real time, or is it the kind of diagnostics where I think logs get written and then sent up to a server that gets analyzed by some group in Microsoft?
Both. So every time you power on your machine, there's a set of information that we log, and there's a service that mines that and looks for problematic behavior. And the question then becomes, what's the service going to do if it notes there's a problem? Let's say you have a driver that's run away and doing some strange things. The simplest thing to do is just to log something to the event log. A more complicated set of things would be to take that, figure out if you can do corrective action on your own, and perhaps self-tune the system that way. Nice. So there's two kinds of diagnostics in the system. There's the kind that we actually actively take the information and then turn that around into self-tuning behavior, and SuperFetch is a characteristic of that, actually. I mean, it's an element of SuperFetch to do that. The other diagnostics are more the type that leave information around for other tools, IT administrators, or even the end user to use to figure out what's been going on in the machine, without a whole lot of corrective self-tuning that goes along with it. So that's how I would divide the line between the two. Excellent.
So from XP to Vista, you guys have done a substantial amount of work in the performance area across the board. Let's dig into SuperFetch a little bit. So what exactly, we had ReadyDrive, as you mentioned, on Channel 9. We talked basically to the hardware side of the problem. But let's focus on SuperFetch and talk about what it does, problems that it solves, and how it works to, at an acceptable level of detail.
Okay. So the reason we built SuperFetch was essentially this. We have a disk on the system that can't keep up with the other components. So random I/O on a drive is typically somewhere around 100 I/O operations per second, which might mean a megabyte per second of throughput. If you do sequential I/O with a disk drive, you might get 20, 40, or even 60 megabytes per second out of that drive. So there's a big gap between sequential I/O and random I/O performance. But even at those higher rates of 40 or 60 megabytes per second, it pales in comparison to doing no I/O at all when everything happens to be in memory. So if you're thinking about improving performance, you're going to be thinking about how to get the right things from the disk and into memory, and how to keep those right things there. And of course, you have to figure out what is the right set of things, and it varies based on condition. To boot your system, you need a set of pages that's different than to play a video game. And so determining which set you need at what time and trying to do the I/O ahead of time so the user doesn't have to wait for that slow disk is kind of what SuperFetch is all about. So it's intelligent subsetting, if you will. The disk is big, 100 gigabytes or 200 gigabytes, or maybe even bigger than that. And main memory might be 1 gigabyte, 512 meg, or even 2 gigs, somewhere in that range. So that's a much smaller pool of memory than there is total drive capacity. And figuring out which things to get before the user actually needs them is really what SuperFetch is all about.
Very, very interesting. It seems almost kind of magic. I mean, I've been noticing in the latest builds I've been running that things are just flying open that I've used before, and it sort of determines sort of patterns that I'm doing. Kind of like machine learning.
Yes.
On a very low level.
In essence, it is trying to match your pattern. So it comes out of the box with a set of information that we kind of like burn into it. We say this is the preceding information that SuperFetch starts with. And after that, it goes purely dynamic. It starts looking at what you're doing and when you do it. So when you come back from lunch, it's got a perspective, seeing you doing that every day, of what you're likely to use next when you arrive back from lunch. the kinds of pages that were there before you left are going to be interesting, plus the ones that you typically use around those transitions are going to be interesting as well. And so it's built up this knowledge over time, and it starts matching your behavior. So we expect over time, instead of getting slower and slower, SuperFetch will help keep the machine running at a certain level of performance, and mostly by picking and choosing which pages to get into memory ahead of time, but also managing the ones that are in memory. So we have a rich prioritization scheme for keeping track of which pages get used. In the old days, when we managed memory, we were managing the set of pages that happen to be in memory. With SuperFetch, we don't just look at that set. We look at the total set of pages that we've seen get used over time. So it's a much bigger set of pages. And we're managing that set. And we're putting priorities on each of those pages and then trying to figure out what are we about to do next. And if we can get those pages in memory ahead of time, or in fact, maybe just keep them in memory throughout the period of time, then we're likely to have a faster, more responsive environment than if we have to demand page fault from the disk.
Interesting. So architecturally, sounds like SuperFetch is a component that's on top of the memory manager? Or where does it live in the
Yeah, I would think of it this way. So if you think of policies and mechanisms, SuperFetch is really a policy agent. Its objective is essentially to figure out which set of pages deserve to get which priorities, and which pages aren't in memory that need to be brought into memory, and which pages in memory can essentially be evicted from memory to make room for the other ones. So it interacts with the memory manager through a set of interfaces that we've concocted. I would think of the memory manager as both a policy agent and a set of mechanisms. SuperFetch uses it primarily as a set of mechanisms, so it controls policy in a large sense. It won't push the memory manager around too much. If the memory manager says we're getting into an unhealthy state, it's got policies that it can use as well. But for the most part, it cedes control to SuperFetch on the client for managing which pages are in memory. And SuperFetch uses the memory manager as a set of mechanisms for getting those pages from the disk through the file system and into memory.
Fantastic. So for the sake of the audience out there, not everyone may be aware of how pages work in the memory. Can we talk just briefly about just the kind of the architecture of memory from a broad?
So it all starts with the file, right? So we have basically a file system, and it divides everything up into files. So you might have a file which has your pictures, a picture or a family photo or something like that. That gets divided into, on the Intel architecture, it gets divided into 4 kilobyte pages. And each one of those pages is what the operating system likes to deal with. We think of this file, at that offset, there's a page, let's go get that. So it's kind of a chunk of the file that we bring into memory. And then we manage things on those 4K kind of size units in memory. So to manage something in memory, that means we have a description for it somewhere. We have a data structure that says, this page goes with that file. And some of these pages can be shared between multiple applications. So there's this notion that, two guys could be using the same thing and they'll share one physical page of memory. And that came from one physical file on disk. But of course, we have thousands and thousands of files on our disk today, and each one of those could be hundreds or thousands of pages within it. So managing this becomes literally millions and millions of different pages, and keeping track of the pages and which ones have the most priority or most likely to be used next is a very difficult problem because it's an enormous problem space. So to manage that, we basically have got time to keep in mind. When are we doing things? How long has this PC been in use? Months, weeks, years? What does this user typically do when they resume from standby? What do they typically do after resuming from hibernate or when they come back from lunch? So we've got a time dimension to go along with this enormous problem space of files and then pages within files. And all of that is what SuperFetch is trying to juggle and manage. And it has to come up with a strategy for what should be in memory before the user actually needs it. Otherwise, it's going to fail.
Very interesting. So now, is there a way to for an administrator, say, to have create policies using SuperFetch for users who haven't even used their session yet? So, in other words, I know everyone who uses this machine is going to launch Office. I know because that's what they do. They're going to launch Office, or the devs are going to launch Visual Studio or whatever, and I'm going to manage this policy for my, 5 computers.
So I'm smiling broadly because it depends what you mean by administrator. If you mean by me, yes. I actually, before we ship Windows, I'm preceding the operating system with a set of pages about the system's behavior that I think are going to be interesting. So when you first get it, it doesn't come out of the box stupid. It knows a little bit about what's important. But then it kind of goes autopilot after that. Okay. And we didn't want to encode ways for another administrator to come along and say, forget what the system has figured out on its own. Forget what Microsoft said was an important starter set. Here's the set of pages that matters most. We didn't want to go that far with the first release of SuperFetch. We felt that if we did that, we were pretty much handing the keys to the car to somebody else, and it was likely to be abused in a way that we didn't like.
Absolutely.
Over time, though, we envisioned allowing others to, I would say, weigh in on the importance of certain pages and certain activities so that they can contribute to the overall priority scheme, perhaps not trumping SuperFetch, however. But we just didn't want to go so far with the first release. So you can see we're going in the direction of allowing users and administrators to have that power. But at first we felt, let's build a fully automatic system and see how we do with that. And then we'll listen to the communities, people who give us feedback on what we should do next with respect to their ability to weigh in on things. Now, there is one aspect of this where an administrator can do some things, though, which is with the Ready Drive thing, where we talked about, I think Rustin talked about this in his Channel 9 interview, where an OEM or somebody who's administering a PC can actually say, I want these sectors from the drive mapped to the non-volatile memory itself. So in some respects, that's a little bit of an out for an administrator if they have a hybrid drive.
Sure. Now, I mean, and of course, being a developer community, Channel 9, is there a sort of a way to program with SuperFetch, or is it purely an internal system component?
At this, we'd like to think of it as purely an internal system component. I mean, it is possible that somebody could basically say, I'm going to try and game the system by touching the pages that I think are most interesting all the time. But that would kind of work on XP anyway. But you would be doing that at the detriment to other things. So we really don't want application developers to program in a certain way. We want them to write applications that make sense from a performance perspective on XP and on Vista. And on Vista, you just happen to get a little boost because something else starts recognizing the pattern and starts doing things before they're actually needed.
And that's SuperFetch.
That's SuperFetch.
Excellent. So, I mean, I think it's clear, it's important to iterate or reiterate that this represents a significant step forward technologically for Windows as a system.
It does.
It's getting smarter.
Yeah. Over time, the PC should be able to figure out the patterns that make sense and optimize for those. In the past, we were very much a demand-driven system. So there's this concept of demand paging, which is what all the operating systems essentially, once virtual memory was introduced, demand paging came along with it. And essentially what that means is an application or a program touches a file and a page within that file, and the operating system says, well, based on that demand, I'll go get it from disk. So that's a very reactive mechanism for managing memory. It's waiting for the demand and then it's acting on that. And SuperFetch kind of transitions to a different reality where we say, we really don't need to see the demand. We've seen the history of things that have been done on this PC and we can anticipate what's likely to happen. So we proactively try and get the system into a balanced or poised state, and that then maximizes the likelihood that pages that are going to be needed from a demand perspective are already in memory and therefore they're available at very low cost as opposed to going to disk. And remember, the differences here are pretty substantial. A disk can do random I/O typically at around 100 I/Os per second, which might be 1 megabyte per second. And we do lots of random I/O because, remember, this is 300 gigabytes or 200 gigabytes. I mean, the likelihood that the diskette is already where it needs to be for the next I/O is pretty small. Typically, we do random I/O. And so that means we can do maybe 100 I/Os per second with about a 10 millisecond seek or so. Maybe 120 if you have a really good drive. But that's a very small number compared to a processor which might be able to do billions of instructions per second.
Absolutely.
Not just cycles per second, but literally, as we go multi-core, you're going to see more and more billions of instructions be executable in a given period of time. But that doesn't mean that you'll do something useful with them. If the stuff isn't in memory, you're likely going to be waiting on that disk. So sucking things from the disk into memory ahead of time and then maintaining that right set becomes even more important as the processors continue to distance themselves from the disk.
Absolutely, that's an incredible point. Because as we move into multi-core, from a programming perspective, we're working on a whole concurrency problem. I mean, the industry is, but seldom do you really think about the hardware.
It's a big concurrency problem, not a little one.
A giant one.
Yes.
And there are people doing some very innovative things, but it's a great point, the fact that the disk is still going to be the bottleneck.
Yeah.
I mean, Intel just promised 80 cores, right?
Yes, they did.
So 80 cores in 5 years. In 5 years, are disks going to be able to handle that? I mean, are they going to be able to match the power with the seek?
Well, they won't. And the other thing that's transitioning, though, very rapidly at the moment is the introduction of flash into the non-volatile memory is showing up in big ways. And Vista has two ways to utilize non-volatile memory. One is as a hybrid hard drive, which is essentially a pool of non-volatile memory, probably relatively small compared to the drive. The drive might be 300 gigabytes in size, but you might only have, say, a gigabyte or 500 meg of non-volatile memory as a buffer. But that's going to happen with greater and greater frequency. You're going to see these caches show up. And the reason they show up is that drives are not only satisfying read requests, but they're satisfying write requests. And in mobile systems in particular, the drive is essentially kind of a power-consuming monster, spinning all the time, spinning at a very fast rate. And in order to spin it down, you need to have both the right set of pages in memory, or in that non-volatile cache, and you got to be able to cache writes somewhere. So that non-volatile cache becomes a very important place to locate writes. So I expect these caches, not just in the drives but elsewhere, the non-volatile ones, to grow in popularity. They're going to show up more and more, and the cost per bit of flash is dropped below that of RAM already, and is continuing to accelerate. So we're going to be seeing very, very large pools of non-volatile memory. Probably we'll have PCs with a pool of memory that's smaller than the pool of non-volatile memory, and that's going to be, again, smaller than the pool of total disk space. So managing all three of those things becomes pretty important. So we talked about one of them, which is the hybrid hard drive being one pool of memory. The other one is the USB key, or you can use an SD card or a compact flash card or any other non-volatile piece of memory that exposes itself to the operating system in a trivial way, just as a volume essentially. That can be used as a cache to accelerate performance as well. Again, buffering against disk accesses are what these are all about. It's not just that they're non-volatile, it's really that they're cheap storage sources that are faster than the drive at random access. And that's what we use them for. So I expect as the cores get faster, or the cores get more numerous and the processing capacity gets bigger, you're also going to see the amount of non-volatile memory or cheap flash access essentially grow in size as well. And then the drive will be used less and less because we'll have this intermediate store that we can put things in. And so then you have to figure out, well, what should be there? It's still an intelligent subsetting game.
Sure.
It's not as big as the drive itself. Something needs to be there, and something else needs to be in memory. And SuperFetch has kind of expanded into the space of managing caches of different latencies. So it has a knowledge about what it should precede into that non-volatile cache, and we've got management logic to keep track of that as well. And that's what ReadyBoost is all about. It's about managing that cache after it's been preceded by SuperFetch.
Outstanding. And your team built that as well?
Yes.
All right.
Yeah. Which was a very fun project.
Really? So we should talk about both of them then. I mean,
Okay.
They're based on similar algorithms, I would imagine.
Yeah. So I guess from a development standpoint, we kind of structured things a couple of different ways. We looked at it and said it would be nice if they started with access to the SuperFetch database. So if it's a hybrid drive or it's a USB key, I plug in a 2 gigabyte USB key. We can put a lot of information on that. What information? Well, the SuperFetch information about which pages are most important, that's a good starter set. But we also thought it'd be good if these things could act independent of SuperFetch as well. Because of where they're located in the system, a hybrid drive and one of these USB keys is actually dealing with sectors as opposed to file and file offset. So when you think about doing I/O in an operating system, what happens is initially it starts as, I want to open this file and I want to access byte 5000 from it. So we translate that into, here's the file, here's the offset with the file, and then as we push the I/O down the I/O stack, that translates into disk sectors that are needed, logical block offsets from the drive. Both the ReadyBoost and the ReadyDrive caching logic is below the file system. So really what they deal with are essentially sectors on the drive. They think of the world as, oh, okay, you need sector 23. Great, I'll go get that for you, if they have it in their cache. Whereas SuperFetch deals with the world as essentially, I've got this file and I need this offset from the file. So it's logical offset from file versus physical location on drive. And if you've got caches on both ends of the file system like that, then you can do different optimizations. And so when we built ReadyBoost and ReadyDrive, we felt that since we knew physical location, we could exploit some optimizations there that we couldn't necessarily with SuperFetch, who really doesn't know where it is on the drive. They just know file and file offset. And so because of where they're located, we thought it's good to share knowledge about information that's important, but it's also good to be able to work independently and exploit optimizations around physicality and other such things. So they kind of start off together, they get themselves in sync, handshake up to a certain point, and then they can run independently.
Very cool. Very cool. So one of the questions that comes up would be, since you're monitoring behavior, that in itself must have some sort of performance implication.
It does.
Okay, so how did you get around that? I mean, it's a hard problem.
Yeah, so essentially the game is this, right? You reference the page, I need to notice that. So there has to be a mechanism for me to record that information. There has to be a mechanism to actually get wind of the fact that you touched it as well. Yeah. So we have a very low priority thread, and we do most things with SuperFetch using low priority. We use idle cycles, and we actually have just a small little tracing thing where a page gets referenced and the memory manager pushes a set of buffers to us. And those buffers represent this page got referenced at this time. We've got other sources of information as well about, is the user present, is the machine going into standby, etc. This contextual information. What are we about to do? What did we just do? That information is also being recorded. Mm-hmm. So we've got page reference information, and we've actually got activity going on that gives us the rich coloring of what we're trying to accomplish. that has to be recorded. That has to be kept in a repository of sorts. We like to call it a database, but it's not a real database. It's just a repository of information. We do most of this with, actually almost all of it, with very low priority threads. And whenever we bring things into memory, we also do low priority I/O to bring them into memory. And the reason we do that is because we're speculative. And so if we lose some information about a page being referenced, it's kind of okay, because if it's an important page, we're likely to see it again. And we're not likely to be in a situation where our low priority threads aren't going to be able to get some CPU cycles to keep track of this information. But it does come with a cost. I mean, it takes memory to store this, it takes some disk space to store this, and it takes some CPU cycles to record all of this information. That has to be offset by the wins we get by having these costs there.
Certainly.
And that's essentially the game, right? I mean, we're trying to beat the disk. We're using CPU and memory to beat the disk, essentially. And on machines with large amounts of memory, managing memory effectively turns out to be a much bigger win than the small cost it takes to measure things. Just to give people an idea of what kind of costs we're talking about, it's well under 1% of CPU over the lifetime of your PC. We're using very, very small amounts of CPU to record things, and well under 1% of overall impact to the system performance. However, it's a chunk of memory. If you go take a look at the SPC host that includes the SuperFetch service, you'll notice that that's a pretty sizable one, and that's essentially the in-memory representation of our data structures to keep track of page references. And so, if you think about a 512 meg machine, we might be stealing 10 megabytes from you to do this. If you think about a gigabyte, that might be 20 meg. And the reason it's that large is, well, we're managing not just a gigabyte of memory, we're managing all the pages that you've referenced over time and trying to be smart about what should already be in memory, which things should we protect, etc.
Absolutely. Now, as time goes by, though, right? So let's say I've been running for 4 years, okay, or 3 years.
It has abilities to prune out old information. Yeah,
so it's being intelligent about pruning. So it's not going to be like the old page file that gets so gigantic, your machine starts slowing down. Which brings up a good point. I mean, really what you're saying, and you may not be saying this, but what I'm hearing is that the days of the system getting slower over time could be ending.
They're improved. I don't think they go away completely. So why does a PC get slower over time?
Let's talk about that.
Question, right? So the classic performance issue with Windows is that they buy a PC, a user buys a PC, they bring it home, they're pretty happy with the performance of it, and then over 6 months, a year, usually more than that, but some period of time extends, all of a sudden their PC is not performing as it once did. And what's happened is they've collected some cruft from the applications, the websites they visited, the little cookies that got downloaded, etc. And there are lots of applications that people use. So the problem one user might have could be very different from another. But essentially it's associated with collecting new things. The issue on XP, I should say there are many issues on XP associated with this, but one of them is the inability to differentiate the cruft activity from actually their applications that they consider useful. So you might go away for lunch, for instance, and an anti-spyware program might wake up, and maybe I shouldn't call that cruft, but it might wake up and do a scan of the drive. When it's finished doing that, it's probably replaced memory with things that it scanned. And it was just trying to go look for things that could be contributing to other issues that you might have in your system. So it's a good program, trying to do a good thing, but at the end of its operation, it's left memory in an interesting state. Whatever happened to be the last set of things it looked at were the most recently used things, and therefore they're likely to be the things that are still in memory. On Vista, that problem will go away because we know that you weren't there, we know that this thing was active, and we're going to protect the pages that you typically like to have in memory from this activity. And so that part of the regression over time, we've done a great deal of work to address. However, you still have more programs on your system at day 3000 than you did at day 1.
Certainly.
And that stuff's not free. I mean, more files on the system, more programs that are active, they'll consume more memory, they'll issue more disk I/O, and that activity is going to go on. So SuperFetch is not a complete answer to the regression over time, but it does do a great deal to actually keep things much more consistent so that you don't feel as though your system is slowed down as much at day 3000 with Vista as you would with XP at day 3000. But it still will be slower then if you've added more software. So, I mean, it really comes down to what did you add, what activities does it actually need to do, and how well can we differentiate its activities from the real user's activities.
Fantastic.
And there's a lot of work that's gone into that space.
And that brings up a great question. I mean, how do you know that the user is running application X and not a service, not some sort of automation, not some sort of,
Well, the easiest is, of course, keyboard input or mouse input, right? And am I in a screensaver or am I not, et cetera. So that's one easy way to look at it, right? So we've got hooks all throughout the operating system that are giving us information about the user's presence, their activities, et cetera, versus these other things. And there's a difference in the way applications work as well that we can discern. So, but mostly is the user there. That's the simplest one of all. And which apps are the foreground one and which ones are not. So a background service is not ever going to be the foreground application. That doesn't mean it's not an important background service. It could be that the foreground app is asking it to do some things. So you have to be kind of clever in figuring out, do you want to penalize that background service a whole lot or not? Because if it's in use at the same time that the user's there, that means something different from it's in use when the user's not there. And of course, it's still different from it's actually the foreground app. So we have to differentiate a number of different ways.
Certainly. And so if an application launches another application, so the user launches application A, which launches application B, that you're clearly smart enough to figure out that B is associated to A, and the user's launched A. So the next time user launches A, both of those pieces in the paging will be SuperFetched.
Yes.
Now going to become a verb, which is very cool.
Is this going to be a verb?
I hope so.
Okay.
It's SuperFetch.
Well, we're excited that they trademarked the name. We thought that was a pretty interesting thing too, right? So geeks get excited when little things like that happen.
That's very cool. So let's talk a little bit about fragmentation in the disk. I mean, since we're talking about performance over time, and why does that always happen? I mean, it's an interesting. I mean, the average user is going to really wonder, like, why do I have to run the disk defragmenter? I mean, I know I've installed all this stuff on my system, and I kind of know how a disk works, and the data is distributed all over it and stuff like that. But
so there's multiple things there. So there's XP did some things about fragmentation automatically. Vista does some things that are more aggressive and more frequent than XP, and it does a better job at the end of the day. But then there's the root cause of fragmentation. So let's start at the root cause of fragmentation. Typically what happens is this. An application creates a file, and they don't tell the file system how big that file should be. So they say, you know what, let's just create a file. The file system says, well, you didn't give me any information about how big to make this, so I'm going to place it here. Now, you picked a location on the drive where you thought there was plenty of free space around it so it could grow a little bit. But how much? Are you going to grow that file by 10 bytes, a megabyte, 300 megabytes, or a couple of gigabytes? The file system has no knowledge of what you're about to do. So when you do grow it, and you grow it by, say, 300 megabytes, and it doesn't fit where the file system initially chose to put the file, now it's got to fragment the file. It's got to say, well, I'll put a piece of it here and another piece way over here. Now, it knows this. It knows it's broken it into two pieces, and again, it might break into 3 and 4, etc. It then knows it's got a problem that it might want to address through defragmenting. Now, so what can the apps do? Well, the apps can essentially ask the file system to pre-create enough space to allow for the growth that they anticipate. And we ask apps that are going to clearly create big files to create large spaces for them initially, and then grow them in big chunks as well. Don't grow byte by byte, grow in reasonable sized chunks. And what this does is it minimizes the likelihood that the file system will place you in a place where it then, when it has to grow you, has to create a second fragment for you. So it's really about what the apps are asking the file system to do, and the file system taking a guess at, hey, where's a good place to put this file? And because there are so many files created by so many apps, and most apps aren't expressing how big they expect the file to eventually be, the file system makes choices that end up producing fragmentation. So there's work that you could do in the file system to try and always put files in places where there's huge amounts of empty free space. But in doing that, you end up creating large gaps between files, and when you have to seek, the seek distances get bigger, and the longer the seek distance, the longer the seek time. So you really don't want your file system doing that either. So there are actually two schools of thought on what to do here. One school of thought says try and pack everything as close as you can all the time, and at some other time make sure you're defragmenting on a regular basis so that you can undo the damage associated with trying to compact stuff. And another school of thought says, no, leave lots of space, and that way you won't have fragmentation. But unfortunately, you'll have long seek distances that you have to deal with. And then you compact later. We've pretty much got a middle ground approach. We try not to find locations that are hugely empty to place new files. We place them where we think there's a reasonable room for growth, but it turns out that fragmentation still happens. So then the defragmentation process has to kick in. On XP, we did not schedule an automatic defrag across the whole disk. We would defragment some set of files, though. So the ones that were used to boot the system, the ones that were used within the first 10 seconds of starting a process, those would be gathered onto a list, and we would defragment those on a regular basis, and hoping that that small subset of pages would basically, of files, would end up giving you a big enough win. The user still then, if they wanted to defragment the whole drive, had to use the utility to do it. So on Vista, not only do we do the same kind of like subsetting of pages used around application launch and boot, but SuperFetch is actually contributing to that list as well. So the list of files that look interesting, that should be near one another and near the outer edge of the disk where we get the best performance, they're collected, and we tell the defragmentation program at once every 3 days, go take a look to see whether you need to make an adjustment to this list of files. So that's a very lightweight operation relative to defragmenting a 300 gigabyte drive. Here's a list of maybe 1,000 or 2,000 files. Go make sure they're placed well. And many of those files never grow or shrink in size, so once they're placed once, we don't have to do work on them again. Now, in addition to that, there is a scheduled task that's run on Vista by default to periodically defrag the whole drive. And when that's done, it's done basically as a background task, and if the user comes back to the machine, it will stop. So we're trying to defragment your drive, but we need time to do it, right? So if it's a mobile system and you constantly go into a standby state or a hibernate state, it won't wake up the system to defragment the drive. But if it's a desktop machine or it happens to be left plugged in overnight and it's a mobile system and it hasn't gone into a low power state, it will get a chance to do the whole thing. And like I said, it's trying to get out of the way of the user, so if you come back, it'll stop quickly. And because it's running when you're not there, SuperFetch has prevented those pages that it needed to defragment the system from really eroding out other pages that you would find useful. So we tried to make it all work together, but I still fear the case where the user's basically not left their machine up long enough for defragmentation to complete. So it's not a bad idea for users to essentially check periodically, once a month, once a week, whatever they seem comfortable, just to see whether they need a defragment or not.
Fantastic. That's really very interesting. I mean, I've noticed that Vista has actually increased performance. One of the things I've noticed, you mentioned Hibernate. Now your team works on with that. I mean, there's clearly algorithms involved in before you hibernate, write everything to memory. Let's talk really briefly. How does Hibernate work? What have you done to which is you hibernate really fast now versus XP? It seems faster to me. And then you wake up.
It all
faster.
depends.
It all depends.
Yeah.
So let's talk about that first.
So I'm going to use intelligent subsetting again as the key term. So let's think about what has to happen in Hibernate. Let's say you bought a brand new laptop. You went to Dell's website, Sony's website, whatever, and you bought a new laptop and it came with 2 gigabytes of memory. You're in good shape. That's a lot of memory. Things should run well there. Well, Hibernate is the process of taking what's in memory, compressing it, and writing it to disk, and then turning off the machine so that no power consumption is going on. So it's a complicated grab set of pages in memory, compress them, and take them to disk sequence. If that's 2 gigabytes of memory that you're going to take with you, it's going to take a long time to take it, compress it, and write it. Pages typically compress about 2 to 1, so essentially you'd be doing about a gigabyte of disk I/O just to get into the Hibernate state. That's clearly too expensive for us to do in a short period of time.
Sure.
So instead of doing that, we try and pick and choose a subset of pages. Again, intelligently looking to see which pages are we likely to need both to get down into the Hibernate state and back up and be responsive when we return. So we're going to try and pick from that 2 gigabytes a set of pages to take with us. We're going to compress them, and then we're going to write them to the Hyper file. And then on resume, hopefully we've taken enough with us so that the system's not in a really tough state where it has to page in a lot of things subsequently. But we haven't taken too much to elongate the actual time to go down. So we're trying to find a balance between how much to take with us, because if we don't take enough, literally, when we come out of the Hibernate state, if we haven't taken enough, then you might be running on a machine with 2 gigabytes of memory, but you might only have 100 megabytes of it with useful pages. That other 1.9 gig is going to come in at a very slow rate, either through demand paging, because we haven't had a chance for SuperFetch to populate yet, or it's going to be at the rate that SuperFetch populates memory, and which could be minutes in the gigabyte cases. So what we try and do is find that balance, and it's intelligent subsetting. So how do we do that? Well, we record every time you go in and out of Hibernate. We pay attention not just to the pages you need to take with you, but also the pages you use on the other end. So we figure out what set of pages should be there. Plus, we take a set of pages that we consider to be high priority pages. And a high priority page is one that you reference with great frequency when you're around. That set of pages is essentially going to be identified and tagged as key pages to keep in memory under almost any load, but also key pages to take with us to the hyperfile, because when we come back out, in all likelihood, they're going to get referenced. And you can expect those pages to be common pages from the registry, common pages from the core system DLLs, common pages from drivers, etc. That's the set of pages, and they mostly get determined through dynamic monitoring of what's going on in the system, and a few of them actually get burned into the system initially by me when we precede the system for setup. But essentially, that's the game. Intelligent subsetting again, right? You can't take everything, but you want most of it when you come back. And then, of course, after we resume, we try and aggressively populate memory from that. Now, there's one other thing we do with Hibernate that's a little different than before.
Okay.
There's a class of Ready Boost devices that are being developed now by manufacturers that are essentially going to be internal to the mobile system or internal to your desktop PC. So it's not going to be one of these USB key things that you can remove from the system and take away. Mm-hmm. If you have one of those in your system, it will essentially be marked for us as a non-removable Ready Boost device, which means we can trust the contents across the standby or across the Hibernate transition. So that gives us an extra cache of non-volatile memory that we can put key pages into. So when you go into that Hibernate state, even though you've taken a subset of pages with you to the disk, this thing could have gigabytes of data pages available. So when you resume from Hibernate, instead of having to page fault from the disk or for SuperFetch to populate from the disk, it can populate much more quickly from this. And these things are going to be very fast. The internal versions of these, instead of being like a millisecond to get 4 kilobytes, which is what a USB key typically is, somewhere around 800 microseconds to a millisecond, instead of being that, it's going to be about 50 microseconds for us to get 4 kilobytes. Now you compare that to 10 milliseconds from the disk, 1 milliseconds for this, or 50 microsecond access times, you can see that the internal versions of these are going to be extremely fast and very popular, and they're going to be very big as well. So in that case, the resume from Hibernate and the subsequent population will be very fast, almost lightning fast, because there'll be no disk I/O involved.
So when you say the internal versions of these, you're talking about the Ready Drive or the hybrid disk?
No, I'm talking about so this device.
Let's talk about that.
So this device here, if I plug it into my PC, this is a USB key, right? And of course this SD card, compact flash card, they're all what we consider to be external forms of the Ready Boost technology, and that means that we might have them get removed on us at any given time. So if a user pulls this out of their PC, we better not have anything on here that we need, because it's gone from us now. So as a result, we only put copies of things here. This essentially is a copy or a redundant copy of something that we've already got internally, either in memory or on disk. It never has a unique copy of anything. Now, when we go into a Hibernate state, somebody might pull this out on us too. And then can we trust it if it shows back up? That becomes very questionable for us. We've decided in version 1 of Ready Boost not to trust the contents of this if we can't see the device at all times. So if we drop into standby, or we shut down the machine, or we go into Hibernate, our driver's not able to monitor this device and isn't able to detect if it's been removed. So we never trust it in those cases. An internal version one of these, something that the OEM has basically put onto the motherboard, can't be removed without our noticing it if we're in a standby state or a Hibernate state. Now, we won't trust it across shutdown because somebody might open the system and pull it out. But in standby and Hibernate, we still got our driver running. We still can pay attention to this device hasn't left anywhere. And if it's been marked by the OEM as an internal version, then we can trust the contents across standby and Hibernate. And in the Hibernate case, that's very interesting because, again, we've taken 2 gigabytes of memory, perhaps, for your laptop, shrunk it down to maybe the most important 200 meg, compressed that and wrote that out. We resume, and now we've got 200 meg plus whatever number of gigabytes we've got in this. And that's a much faster post-resume experience than if we have to go to the drive. So that's part of the story too, and we expect these to show up in great numbers because, again, I think the cost of flash is dropping so fast and the capacity is improving. We're seeing basically a halving of the price every 12 to 18 months, and we're seeing a doubling of the capacity just about the same time every year or so. And that means, of course, 2 gigabytes today at 40 or 50 or 60 bucks is going to be 20 or 25 bucks next year, etc. And the performance of these internal versions, because they can be attached to PCI Express, is quite a bit better than if they get attached to a USB bus. It's mostly about the interconnect latencies, not so much the flash. So
very cool. So, as when people buy a new PC that's going to have Vista on it, there could be, for example, hybrid hard drives built into those machines.
Yep.
Right? And that's going to be an automatic performance win for people running. I mean, the operating system has to be smart enough to take advantage of it, and that's what you guys have done with your Ready Star technologies.
Yeah.
Which is very cool.
Yeah. So, I mean, the PCI one is one, mobile or desktop, is one that has probably 2 gigabytes of memory, just because memory is a great thing to buy, and the price of that is dropping. Probably 4 gigabytes of a Ready Boost internal type flash, because that's going to give me, I get 2-to-1 compression on that, so that'll give me 8 gigabytes of buffering against the disk. And then I want a hybrid hard drive as well. And the reason I want the hybrid hard drive is because, unlike a Ready Boost device that is caching copies of things for read benefits. A hybrid hard drive can spin down and use the flash it has to cache writes. So I can get a quiet system with a drive spun down, caching writes. I got these two pools of memory, the hybrid hard drive flash memory, the ReadyBoost pool, I should say pools of flash memory, the ReadyBoost pool of memory to cache up to 8 gigabytes worth of stuff. And then I've got a pool of RAM as well for the very low latency access requirements that a processor needs. And to me, that's a PC where I won't go to the disk very often at all. It'll be very quiet, very fast, and it's not going to be terribly expensive as well because flash prices are dropping so fast.
That's amazing. And as you mentioned earlier, it's going to have impact on the lifetime of batteries.
It will.
Because it should spinning disk.
Right. It should have longevity improvements for the drive because it won't have to be doing all the seeks and spin ups and spin downs, as well as the battery improvements for the mobile systems as well. So
very cool.
All good stuff. So we think we're ready to go with all this, which is good. And it's very different than XP. And it should be a quieter, more power-friendly environment across the board. At least that's what we hope.
Absolutely, and more performant.
More performant as well.
I mean,
this is why that stuff's being done on the perf team, right? So make sure that all the algorithms and stuff like that are working actually and do give the perf boost. And we see lots of demos. We expect many more demos. Our partners, especially the ones building these devices, they're constantly knocking on the door saying, do you have any great scenarios that we can run? We want marketing fodder. We want to be able to go out there and market this stuff and say, well, yeah, there's plenty of them. And you'll start seeing them more and more, especially as people start building these faster and faster devices. They're going to say, look, you plug this into Vista and here's how your performance changes. And so the before-after type performance numbers are going to be pretty ubiquitous.
Absolutely. Now, I mean, and for the general user that's going to upgrade XP to Vista as opposed to buying a new machine, they're still going to experience a performance gain based primarily on SuperFetch. I mean, because they use the computer the same way all the time.
Yeah.
Is there any data you can gather during the upgrade process? I mean, is there any information on the machine that can tell you how this person is using the machine?
No.
Okay.
So unfortunately, you go through that upgrade process, and what you're going to start with, I shouldn't say unfortunately, it's not going to be so bad, but after you go through the upgrade, you're going to start with essentially the preceded knowledge about what we think Vista will run well with. So you get that starter set of tuned information. And then from there it goes purely dynamic and starts monitoring your behavior. It doesn't take long for it to start making a big difference, but it definitely has a little bit of a startup thing. So the first boot isn't as fast as the third boot, things like that, right? I mean, it starts to get into a groove pretty quickly.
Fantastic. And one of the things that a lot of people interested in operating systems dream about is actually an intelligent operating system where it self-maintains. It learns, right? It learns from what's going on. It doesn't prompt the user that it's learning and that, hey, do you want me to learn this? Yes. Yeah. It just learns about itself. It sees what's going on. And it sounds like the technologies that you've developed in the Vista wave, or the Vista iteration of Windows, is sort of the beginning of an operating system that actually could be homeostatic.
Yeah.
And when things happen that are bad, it counteracts them with feedback in whatever direction it needs to be, and the system just gets better.
So, I mean, you won't see any user interface for SuperFetch. It's all very plumbing underneath the covers doing the right thing. That doesn't mean there isn't value to go after developers and try and come to some agreement about how best to allow them to play in this space. Imagine you bought a new version of, I'll pick Visual Studio because it's a pretty sizable thing, but it could be any sizable operation. And it actually came to the table with preceded knowledge about the set of pages so that they had a better out-of-box experience with that application right away. I mean, that's the kind of thing I could see us working with developers to kind of improve an understanding on. The only thing we were afraid of in version 1 was essentially going too far with this new technology. It made sense for us to take a measured approach, do as much as we could automatically, make sure all the self-tuning algorithms and stuff like that work the way that we expect. And then as we go to the next step, we probably will bring in developers, and they'll be able to participate not just in introducing, some information that we can use to help weigh pages, but potentially in developing some new capabilities as well. So
fantastic.
I look forward to doing that, actually. It'll be kind of interesting.
Great.
We have a lot of the infrastructure actually to start working with people now. It's just a question of what are we going to actually expose and when are we going to do it.
Fantastic. So let's talk a little bit about you. You're a distinguished engineer, which is a prestigious honor here at Microsoft.
It is. Thank you.
Congratulations. Now, what does that mean exactly? So you run a team. So you run a team of architects, or how does it work?
So what is
anyway? Let's go back.
Meaning?
Let's go back actually to my original question, which is that's your title and everything. But I mean, you've been at Microsoft probably for a while. I mean, you've been working on operating systems. So tell us a little bit about your history.
So I started working on operating systems in graduate school at Ohio State, on Sun workstations and HP workstations, all Unix fun. And I took a job upon graduating with IBM to work on AIX. So I learned an awful lot about the inner workings of operating systems on the Unix platform. And then at IBM, we were forever in the business of trying to come up with better new designs for operating systems. So all sorts of crazy ideas, actually, and learned a great deal about operating systems performance as well as operating systems architecture there. The commercially successful versions of operating systems at that time, included some Unix variants, but clearly Windows was moving very fast and had a huge share, and it became a very compelling thing to work on operating systems performance that was going to be reaching hundreds of millions of people as opposed to tens of thousands. So I made a move to Microsoft probably about 10 years ago, predominantly because I wanted to have a larger impact on the industry. So what does it mean to work in Windows? Well, I mean, we have the most complex set of applications that run on this platform. They vary from high-end CAD/CAM applications to little tiny media playing things to applications like Notepad. But they all bring something to the table, and to build a general-purpose operating system that can operate for all of them in an acceptable fashion is quite the trick. And to make performance or keep performance moving in the right direction as hardware changes is also quite the trick. Now we're fortunate to have a lot of devices, but devices actually come with, or I should say, a lot of devices and a lot of device drivers come with performance issues too. So the architecture's got to be sound enough to be reliable as well as performant, and that actually becomes part of the challenge. So one of my team's missions is essentially to continue to be pushing the platform forward so that it can continue to maintain a high degree of performance and improve reliability and improve security all at the same time.
Wow, that's awesome. And that Vista's the first step in that, snapshot in the iteration of Windows coming out. I mean, as Windows evolves, all these things are going to get more advanced, and things are going to get more performant. Perhaps the architecture of the system will change a little bit.
It will continue to change. I mean, Vista's a big step from XP with regards to security. And when you think about improving security on the platform, you're basically adding checks in certain API paths, and that usually comes with a performance penalty. In this case, we added an awful lot of new processes. So we separated out our services so that the ones that needed access to the network and could run with restricted tokens were separated from those that didn't need access to the network, et cetera, et cetera. So we broke up the number of services we have into many smaller little buckets. And as you add processes, you add a performance penalty on the client space. And so, we have to offset those performance costs with performance gains somewhere else. And so security is one of those areas where the platform has advanced tremendously, and we're very happy with that. But it came with a performance cost, and we had to offset that with wins elsewhere. And I think you're going to continue to see more and more security enhancements added to the product, as well as more features like, search in this release and desktop window manager, the Arrow experience, et cetera. Those things add improvements for the user, but they come with a performance cost in some cases. And so that means we have to look for new ways to improve performance. And in this particular release, it was a lot about managing memory and adding new kinds of capabilities to the system with Ready Boost, Ready Drive, et cetera.
Fantastic.
And the self-tuning diagnostic stuff.
Outstanding. Well, thank you very much for your time.
Sure thing. Thank you.
We've learned a lot about these very interesting technologies, and we'll continue to focus in on this as we move forward from operating system to operating system.
Okay.
Thank you very much.
Thank you.